Yeah, wait 1 minute. Actually, I'm facing a problem with the sharing option. So just again, once again, I'll share you. Please wait for that. Yeah, and I hope it is visible to you. Yes. Yeah, actually, we discussed yesterday the different types of crystal systems as per angle, how the axis are travel through this center point through the center. Once again, we get a recapitulation of these things. Cubic system. If you go into the cubic system, this system, it has three. Yeah, it has three crystallographic axis. All three axes it's equal length. It has the equal length. Just you can see here. That's A1, A2, A3. All are in equal length. All are having an equal length. So that, and not only that one, it's one to another. It's intersecting with 90 degrees. It's intersecting with a 90 degrees. So that A is equal to B is equal to C is equal to the axis names. A is equal to B is equal to C is equal to 90 degrees. Then next one. Next one, it is a tetragonal system. In a tetragonal system, you see here, the system, it has a three crystallographic axis, same as we saw. AB or it's a horizontal axis and which are having a equal length. And C, it is a vertical axis. It has a vertical axis and it's a longer or shorter than the A and B axis. The C axis make an angle with a 90 degrees with each other, definitely. But in a, as per lengthwise, it is a lengthwise. Here there is a differentiation for a when we see the as per length, it is a having a length when you compare with C, when you compare with AB, the length it is the height. Or sometimes maybe it is shorter also. But when you come into the angle wise, as per angle that is called A is equal to B is equal to C is equal to 90 degrees. Let's we know that. And next one is orthorhombic system. In a orthorhombic system, all the three crystallographic axes are unequal here. Here, these are already unequal. The axis lengths are different, but the angle it is the same. The angle it is the same. It is intersecting all the axes at 90 degrees. It's 90 degrees. Here the axis it's a sharp and it is known as the brachyaxis. You see here the small axis. The small axis. The small axis it is called as a brachyaxis. And the B axis sometimes maybe it is a long and it is called as a macro axis. B axis, you see the vertical line you can see here, it is opposite the vertical line. It is it's very long axis. I'll tell you that is also. And the diagonal intersecting angle, that is A. And so one more angle horizontally, it will be there. That is B. A, B, C. A cross into B cross into C. So here, as per lengthwise, these are all different. So that A axis it is called small axis. It's very small when compared to the two. It is known as a brachyaxis. B axis it is a long axis. It is known as a macro axis. And the C it is called a vertical. The vertical line you see here, it is a visible to you. The line, whatever it is appearing, the straight, the long line, that is called C axis. It's a vertical axis. Next, coming to the monoclinic system. In a monoclinic system, you see here, it's a one inclined axis, and all the three crystallographic axes are unequal here. But each one, some angles, some axes are, some axis lines are straight above the 90 degrees. For 90 degrees, it has the axis, it has a 90 degrees. In the system, we are calling A, it is called as a clino axis, and it is inclined to the vertical axis, and it makes an angle greater than, or sometimes maybe it is less than 90 degrees. It's inclined with the C axis. Here, the B axis it is called as a ortho axis. It's a right angle. to the A and C axis. And it can be interpreted A is equal to B is equal to C, and it is equal to 90. As per angle, we can talk. Yeah, next one, it is a triclinic. Yeah, in a triclinic system, it has a 3 inclined axes. All the 3 crystallographic axes are unequal, and they make subtle and acute angles with each other, and it can be interpreted as A is equal to B is equal to C is equal to 90 degrees. But when you see here the angles, here we can say that is alpha, beta, gamma angles. Alpha, beta, gamma angles. As per that, we can express the angles, how they were arranged. According to that, the axial planes, how they're traveling through this center point. According to that, we can make express. And one more it is. Yeah. Here actually in a triclinic, the angles may be, that means here, as per angle, if you go, as per angle is not equivalent. As per angle, it's not equivalent this value. So that we can say that is A is equal, B is equal to C, or alpha naught is equal to beta naught is equal to 90 degrees. For our purpose, that means for knowing purpose, the axial elements, it is necessary to know A by B, B by C, or C by B. And the values of these alpha, beta, and gamma angles we will consider. The hexagonal system, crystals actually having the 4 crystallographic axes. Hexagonal system, 3 out of 4 crystallographic axes. This one. 3 out of 4 crystallographic axes, which are in a horizontal plane and which are equal in a length. They are called A1, A2, and A3 axis, and make angles of 60 degrees here. Yesterday I told you that it's 60 degrees or 120 degrees with one to another. The 4th axis is singular and vertical. It's lies normal to the plane and containing the A1, A2, and A3 axis. It is called the C axis. Most of the maximum we can see these angles in a different levels. In a different levels. As per that, we will classify. And final one is a trigonal system. It is a subsystem of the hexagonal system. Here, the both systems have a same disposition of axis, but they are differ in their symmetry. The axis pass through the two corners, and the crystals is belonging to the trigonal system. And so more conveniently, by considering the containing more four crystallographic axis, like in the hexagonal system here. If it is in a rhombohedral form, there are 6 rhombo shapes and 6 rhombo shaped faces, 12 edges, and 8 corners it has. The 8 corners which belongs to the 2 sets. It has a 2 sets. And each one set, it's containing the 2 corners, and other set is containing the 6 corners. The 12 edges belonging to 2 sets. And again, each set it contains the 6 edges. 6 edges. You see here this axis. A1, A2, A3, and the vertical line it will also set, but actually it is not applied here. The axis pass through the 2 corners. It is a singular axis and it is called the vertical axis. Or the vertical axis maybe it is the C-axis. The midpoint of the edges arranged in a zigzag fashion, and it's constituting 3 horizontal axes. These axes are all called the A1, A2, A3. These are on these axes only. What we are observing here, A1, A2, A3. Yeah, some crystallographers, they are not considering the trigonal system. It is an independent system, not considered. But anyway, and they are recognizing only a 6 crystal system. The recognizing a hexagonal and a trigonal depends within hexagonal system only. Yeah, here the symmetry of crystals. Actually, before going to that, some crystallographic notations. We will see that crystallographic notations. I will tell you that. It's a simple method. The notation in this notation, it is a very simple method to express the position of a crystal face, how it is look like with reference to the crystallographic axis. And the parameter system is a wise and the index system of a Miller. There are 2 systems are there. Based on these 2 systems, the crystallographic notations are available. The first one, it is the wise notation. The parameters of unit, the unit phase, whatever it is there, the reference to the axis, that is maybe a crystallographic axis only, and which are considered as 1A, 1B, and 1C. 1A and 1B, 1C, we will consider that is as the A, C, A, B, and C. It's related to the length. So that we'll call A, L, or LA, LB, LC. It is means the length. Length, the axis, how they are passing through the center point, how they are passing through that one. As per that, we will say the axis which are the passing through this one or not. And next one, it is here again, the position of any face, it is indicating the, maybe sometimes it is indicating the faces as per the faces. P, suppose P name, it is the one side of a face P name, it's a P. The other side of that one, it's B, and another side, an additional side, it is indicating as a C, A, B, C. As per these faces on the faces base, it's intersecting and cutting this face through the unit cell. Yeah, it cuts the negative side of a B axis, the distance of 2 units, and it lies to parallel to the C axis. And then we can say the symbol, it is A, 2B alpha. How they are cutting the faces? According to that, we will give the number. When you come into the Miller notation, Miller indices also we are calling this. In the Miller notation, index system of a Miller, it is obtained from the parameter system by Weiss. The Weiss is taking the reciprocals of the same parameters, whatever parameter we are considering, and the same parameters, it's considering as a reciprocals here. The same reciprocals of a parameter is called as indices. We'll call that is as indices. That's maybe what I told you just now. As per the face, that's one side of the P, one side of the Q, and one side of R, whatever. Then one side of P, A, P face, and QB, that's related to the B axis, and then R, it is related to the C axis. So that PA, QB, R. If it is written as a 1 by P, 1 by Q, 1 by R, 1 by R. R, if you consider this as a length, we can also, that is called as a, we can call that is as a L, L by P, L by Q, L by R. If you give the simple name to that one, that's the HKL, where H is equal to 1 by P or L by P, or K is equal to 1 by Q, L is equal to 1 by R. The indices is written in the axial order according to axial order. That's A, B, and C. And there is no mention of an axis if it is made. The same reciprocals of infinity, it is 0. The indices are written as a whole numbers, and punctuation marks are not put between the numbers. So if you can put that 2A, comma, B, comma, 3, comma, 6C, comma, it is indicating as a fish symbol. But in Miller symbol or in Miller index or in a Miller notation, no need to mention the comma or a full stop between the letters. Just simply we should write that is a 1 by 2 or 1 by 3 or 1 by 6 or what else, or 3, 2, 1 like this. Okay, suppose if you're giving the symbol with the number, it is indicates phase symbol. When it's given in the flower buckets, yes, definitely we have to show these symbols or these reciprocals must we have to show in brackets, flower brackets one or braces. When it's given into the square brackets, it is indicate that zone symbol. That's indicate that zone symbol. Suppose if you write the same 3, 2, 1 example, the faces numbers, it's 3, 2, 1. 3 to 1, we should write in within a open brackets or normal brackets. It is indicating as a zone. It is indicating as a zone. Or else, if you can write the same in a flower brackets, the same 2, 3, 1, whatever it is, or 3, 2, 1, 1, 2, 3. If you write it, these are all in a braces or a flower bracket, and that is indicating as a phases. Phases. So here the differentiation we can see. If you write this numbers, alpha numbers or numbers, digital numbers 1, 2, 3 within your brackets, that is indicating is that is indicating as zone. And if you write the same into the in a flower brackets, and that's indicating as the wait, I'll do that. Wait, I'll do that. If an index, if it is negative, it is indicating by marking a bar on the number. Suppose if you can say that is thus 100. It's a Miller symbol of a phases, which is in normal, it's a negative terminal. The A axis and lies it's parallel to the B and C axis. But anyway, when we are going to write as per symbol, and those masters will we have to write within a flower brackets, or sometimes we can show the same, or sometimes we can write into the normal brackets. And let us see the axis of symmetry. Or before going to that, just we see the plane of symmetry. How it is, how we can explain that. Plane of a symmetry is a plane. It is divided divides as a crystal into the two similar halves. Among these two halves, one of the crystal it is the mirror image, and another, the other one, it is reflecting to the previous one. There are two types of plane of symmetries. One, it is a axial plane of symmetry, and second one, it is the diagonal plane of symmetry. In an axial plane of symmetry, the symmetry is a plane divides the two crystals along the crystallographic axis. There are two types of axial planes we have to identify. One, it is a horizontal axial plane, and the symmetry is normally to the vertical axis, and the plane contains two or three horizontal axes. You see here the differentiation, what it is. In a horizontal axial plane, the symmetry plane, it is a normal to the vertical axis. And the same plane, it has a 2 or a 3 horizontal axis. I mean, horizontal. When we are speaking about the horizontal, it should be reflecting 2 or a 3 horizontal axis. And we go into the vertical axis. In a vertical axial plane of symmetry, it is a parallel to the vertical axis, and the plane contains one of the horizontal axis, and it's indicating as the C vertical axis. And second one, it is a diagonal plane of symmetry, in which the symmetry plane divides the crystal at an inclined position of a two crystallographic axis. It's a two crystallographic axis. The diagonal plane O, it contains C vertical axis in the tetragonal and hexagonal systems. And it contains any one of the crystallographic axis. That may be either an A axis or a B axis or a C axis. But these type of a crystallographic axis we can able to identify in a cubic system. For example, you see here, the plane for symmetry can be explained by the taking consideration of a simple cube. We know that how many planes it will be there on a cube. Yeah, exactly. It's the 9 planes. From these 9 planes, 3 are axial plane. We know that one it is horizontal and 2 remaining are vertical. And the rest of 6 planes are diagonal planes. The rest of 6 are diagonal planes. Axial planes of symmetry. A crystal, it has an axis of a symmetry. In a space, when it is going to occupy the position in a space, it's a more than once, it's in a complete 360 degrees rotation. The angle of rotation axis in the crystal system, it is called as the axis of a symmetry. The angle where it is rotated, the angle of rotation in the axis in a particular system. In a system only, it is the angle it will be rotating up to maybe that is a 360 degrees. The 360 degrees of an angle of rotation, it is called as the axis of a symmetry. It's depending upon the degree of a rotation, the rotation axis of a symmetry, and it's a crystal. It may be to occupy the same position into 2, 3, 4, or 6 times until to complete the rotation. If a crystal passes the same position at 180 degrees, 180 degrees means actually we know that the circle, once the angle if it is rotate at 360 degrees. So if it is a crystal, it is occupies 2 positions and so passes the same position at 180 degrees. 2 times its It's taking it 2 times to complete the same run. Then the rotation of axis, it is known as a diode axis because of it is divided into the 2 and it is occupying the 2 angles of positions. Or else we are calling that is the twofold of a symmetry also. Similarly, there are three folds maybe, that is the angle it will be inclined at 120 degrees. And fourfold symmetry occurs at 90 degrees. We know that 90 degrees means it's a 4 parts. The rotation is taking the 4 parts, the angle. So that is the reason the angle length is divided into the 4 parts for each 90 degrees. For each 90 degrees, 4 parts, 4 into 90, 3. And 6-fold symmetry also, it occurs at 60 degrees. Occurs at 60 degrees. Here, given some crystal divided into the crystal system based on the characteristics, axis of a symmetry. Systems and their characteristics of symmetrical properties as given here. Now you see the first one, it is a cubic system. In a cubic system, the axis of symmetry, it has a 4. It has a 4. One, it is a 3. One, it is a cubic system. The axis of symmetry is a 4 3-fold. 4 3-fold. Or 4 triad axis. It's a 4 triad axis. And second one, we see in a hexagonal system, 1 4-fold, 1 4 symmetry, or 1 tetrad axis. Third one is orthorhombic system. In the orthorhombic, it's a 3-fold or 2-fold. The symmetry, or it has a 3 diode axis also. First one is monoclinic. Here only 1 fold is there. Mono means only 1. Or else it is a 1 diode axis. The fifth one is a triclinic system. It's a none. In hexagonal, if you see the hexagonal, it's a 1/6-fold. It's a 1/6-fold symmetry on 1 hexad axis. 1 hexad axis. And final one is a trigonal system. 1/3-fold. 1/3-fold means that's a first or 1 symmetry or 1 triad axis. Next one is the center of symmetry. Every crystal, it has a center and it has a center of symmetry also. It's like the faces, edges, corners, which are arranged in the pairs and which are occupied at irregular position on possible sides of a central point of the crystal. One can observe that a cube has a center and it is having the symmetry, and the tetrahedron, it has no center of symmetry. Next, coming to the interfacial angles of crystals. Oh, here the constancy of interfacial angles because of irregularities imposed on the crystal when in a growing stage. Always the real crystal it may be differ from its ideal or equal by its crystal forms, and it's showing the phases of different in sizes and different in shapes. As much as it's not generally possible to determine the symmetry elements of a crystal forms, yeah, sorry. The consistency of interfacial phase of angle. Actually, what is happening here? When it's the crystal growth, during that time, there are various factors are impacting on the formation of a crystal. So that what is happening at the time, sometimes maybe those having a different structure, shape, and sizes. And they're not having the equal formation of the sizes. But as much as it's not generally possible to determine the symmetrical elements of a crystal at the time if you wanted to study. In spite of that one, we need to study the difference between to the real crystal, what it is that, and what the crystal it is the ideal, and it's the equivalent. For the purpose, the interfacial angles, it's useful to us. And the angles which are between similar planes of a faces in both types of crystals are one and the same. So that the interfacial angles between a pair of faces, it's an angle to the two faces, and it's a make at the center of a crystal, definitely. The angle where it is make, where the two lines it's intersecting, and there the intersecting point it is creating the angle of the two faces or two lines in it. And it's a supplementary for the angle between the two faces. And the measurement of interfacial angle, it is considerable to use in identification of real crystals. As per the law of consistency, the interfacial angles or the Steno's law, the interfacial angles between any pair of two faces in a crystal is identical to the same pair of a faces of any crystal that belongs to the same species. So that here, as per Steno laws, the interfacial angle between the any pair of faces it should be identically the same pair of the same phase, but maybe it's coming from the any type of a crystal. And again, it belongs to the same species. Same species. That means same species means that's the type of formation, it is the same at the time. Next, coming into the, what about the goniometer? Yeah, it's very simple instrument. It's used to determine the interfacial angle. It is called as a compact goniometer. It consists of a protractor. You see here as a protractor, and which to rotatable, or it is fixed in the center. In the center, and at the center point is fixed, and as per the base, it's fixed at a point, and the goniometer, it will be rotating. Yeah, it is useful to determine the interface angle between a pair of faces. It is useful to determine the interfacial angle between the two pairs of faces. Either maybe it is a real crystal, or it's an ideal crystal, or it is a model crystal. And we place at one of the two faces and rest on the base of a protractor, and other thing to rest on the rotatable arm. See that there is not even a slightest gap between the faces. And the parts of the goniometer, you can see there is no gap between the one angle to the another angle. If gap it will be created, the angle it will become wrong. So that no need to mention of a gap, and there is no gap maintenance. So then only we can able to read the angle position of the side of the side of the faces, and it has a rotatable it is shown along with this base. What it is that accuracy. If you wanted to measure that angle, faces angle between the two, with using of this goniometer, the interfacial angles we can measure, and it can be measured to an accuracy of 30 degrees by using the contact goniometer. And this instrument, it cannot be used to measure the interfacial angles of a small crystal. In order to measure the interfacial angles of a small crystal with an accuracy, definitely it is also having the 30 degrees, or sometimes maybe it's a higher accuracy. The optical goniometer, it is used for measuring the accuracy of an angle data. The study of the optical goniometer is beyond the scope of this laboratory, and we are using it manually. And next one, it is a crystal form.
It's a crystal. In a crystal forms all the phases, all the phases of a same size and same shape, if it is occurs in an ideal crystal, and it belongs to the only one formation or one form. The number of phases in a form is depend on the symmetry elements and present in the crystal, and the orientation of the phases with reference to the whatever symmetry elements we are studying. The main concept of this form, it can be best to explain by taking up an example of the human body. It shows the bilateral symmetry. When you come into this crystallographic language, if we can consider the human body to show one vertical symmetry plane and divide into the two halves, one on the mirror image and the other it is original. We know that all of those parts of a human body, that's why I outlined the symmetry plane, which are represented by the only one part only. And while those are lying on either side of a symmetry plane, which are represented by two parts. That's maybe whatever parts we have, those are all these will be indicating on the, and it's reflecting on a mirror, another side. So there are different types of forms. If we see that, one, it is a simple form. This simple form is made up of cases of the same size and shape. Such form, it is known as a simple form. Example for cube, octahedron, bipyramid, etc. A compound form, second one, it is a compound form. A form has a different sets of faces. It is a differ in their size and the shape. This form, it is known as a compound form. It is a different. In a simple form, it is the same. The faces, size, shape, all are equal. Example for octahedron, bipyramid, cube. When you come into this compound form, as well as the form, it has a different set of faces. That is the differentiation. It has a different set of faces, and it's a differ in their size and shape. And this form, it is known as a compound. Sometimes maybe it is looking at a complicated also. At the same example, sometimes the cube is also applicable here. Octahedron, prism, pyramid, and pinacoid, etc. Third one is the closed form. The closed form occurs alone only in a crystal, and it encloses space without aid and other forms. A simple form, maybe it's the simple form, maybe it's enclosed. We are called this closed. It is a closing and enclosed by the crystal. The space without aid, with adding of others. And another one, it is an open form. And open form, it cannot occur alone in a crystal. It's always combined with another form, and it should be enclosed by another one in a space and with a crystal. A compound form may be an open form. Yeah, limiting forms. Yeah, some crystal forms are limited in a crystal class. The limiting forms have a fixed Miller symbol, and they can be obtained. They can be obtained from other crystal forms which have a variable Miller symbol. Suppose they have a very less number of phases when we compare with other crystal forms in a crystal class. For example, the cube and rhomboidodecahedron, which are having the limited forms of a tetrahexahedron, cube, and octahedron, all are also they having the limited form. And these these octahedron cube, it's a limited form. It's associating with a trapezohedron, ectahedron, and rhomboidodecahedron. This is some of the general forms. You see, the forms have a variable Miller symbol and maximum number of phases as in the crystal class. When you come into the general form, it's incorporating all the forms of the same crystal class, and class is named after its general form. For example, if you see the hexaoctahedron, it has a 48 phase. In hexaoctahedron form, in a general, it will become considered as a galena class in a cubic system. And the incorporating of forms like cube, octahedron, rhomboidodecahedron, trisoctohedron, trapezohedron, tetrahexahedron, and known as special forms in the some octahedral class. This all will become under general forms. Just we see some important crystal forms just mentioned here. It's a cube. It's a cube. This is the form. It's a cube. I'll tell you about that is also, but actually before going to that, just we need to know the isometric system, isometric, tetragonal, and orthorhombic. Just I will give you today introduction, and we'll continue in tomorrow class. Yes, we have seen in the previous two classes, that is yesterday and today, how the crystals are classified in systems. Here we see that the isometric, what the isometric, tetragonal, and orthorhombic systems. We see that. We know that isometric system is all three crystallographic axes. The axis lines are equal in a length, and it's a make an angle. It is making angle at 90 degrees with each. In a tetragonal system, is 2 out of 3 crystal axes or crystallographic axis, which are equal. 2 lengths are equal, but when you compare the third one, it is not carbon maybe it is a difference. But the angle it is the same. The angle is making as a 90 degrees in all the systems. Or when you go into the orthorhombic system, all the three crystallographic axes are different in a length, but its making angle definitely it is 90 degrees with each angle. So now just I'm stopping here, and tomorrow we'll continue. Tomorrow we'll discuss the isometric, tetragonal, and orthorhombic systems. So clearly we'll study. We'll say tomorrow that one. After completion of these crystal systems, and we need to discuss about mineralogy, our mineralogy chapter also. That's also we see. Thank you.